Okay, 3 o'clock, gotta talk now. So reminder, a week from today is the first test. You will get, some students keep on asking me, do they need to have a cheat sheet? I will provide you with all the equations and constants. And if you think that I need to add something to the sheet or something you want to know something else, I'll tell you. Like if you forget that milli is 1,000th, I'll tell you that. What I won't do is I won't tell you how to do the problem. Be like, oh, like how do I do this problem? Like, oh, you've got to convert to moles first. Like, no, I won't tell you that. But any equation, constant, data, way of doing thing, you get the solubility rules, you get the how to assign oxidation states, that kind of stuff. So, any questions so far about that? And we're the last class in this room, so you can go over as well. So, I didn't quite figure out what to do about the noon class. Maybe I'll take a chem lab or something. I'll take a chem lab then too. Shoot. I'll figure something out. People that want to stay after. Anyways, so anybody have any questions about anything before we start? So the this stuff, again, the gas laws concepts are not covered on the next test. So, or I'm sorry, it's not covered on the test a week from today. It's covered on the following test. So where we're at right now is we're talking about Dalton's law of partial pressures. So it's all ideal gas law stuff. PV equals nRT. And you can solve for pressure this way. And for mixtures of gases, then it's just the number of moles. So sorry, the pressure of whatever species is the moles of whatever species times RT over V. It's just the same thing, the PV equals nRT, just moving that over like that. And then we get the Dalton's law of partial pressures, that if you mix gases together, that the pressures they exert is just the fraction of whatever pressure they bring in. And if you add them together, you get total pressure. It's probably not surprising for you. Because so if you have 5 atmospheres of hydrogen added to 10 atmospheres of helium, you get 5 plus 10, you get 15 atmospheres of a gas mixture. That's all it's saying. And then the mole fraction is here. And chemistry is kind of weird. Everywhere else, they call the mole fraction in the gas phase Y. So X is usually the liquid mole fraction, but in chemistry, at least Tro says X. Everywhere else says Y. There's a series of laws called the Code of Federal Regulations, and there's a subset called RCRA. They deal with like emission standards, and there's equations in there, and those equations all have Y in them. So most everywhere else for the mole fraction in the gas phase will be Y. Mole fraction in the liquid phase will be X. So, but you won't see that till next semester. And okay, and then the pressure of whatever species is the mole fraction of whatever species times the total pressure. So if I have a mixture that's 50% hydrogen and it's 10 atmospheres, then it's 5 atmospheres of hydrogen. So 0.5 times 10. So, all right, well, let's do this for a problem. So we'll go a 1 liter mixture, helium, neon, argon, total pressure 662 millimeters of mercury at 298 K, 25 degrees Celsius. The partial pressure of helium is 341 millimeters of mercury. Partial pressure of neon is 112. What's the mass of argon? Okay, so the way we're going to solve this problem, what we need is the mass of argon. So we can get that from the moles of argon. And the moles of argon we can get via the ideal gas law. But we don't know the pressure. But we can get the pressure from the total pressure. I'll show you that in a second. Okay, let's draw a picture. Here's my vessel. My vessel looks a lot like a cube, because I can draw cubes. And this is 1 liter, total pressure 662 millimeters of mercury, 298 Kelvin. And in this mixture, we have argon, we have neon at 112 millimeters of mercury, and we have helium at 341. So we need to find the pressure of argon, and we know that the pressure of argon plus the pressure of neon plus the pressure of helium equals the total pressure. Or from that, we can then solve pressure of the argon is equal to the total pressure minus the pressure of the neon minus the pressure of the helium. Is everyone okay with that? Let me go in there. The pressure of the three gases, the total pressure. So if we want to solve for argon, we just take the total pressure minus the other two. And 662 minus 112 minus 341. And we get 209er. And then PV equals nRT. And N equals PV over RT. 209 millimeters of mercury to atmosphere 760. Volume is 1 liter. Yeah. Over R, 0.08206. Put that in our calculator. And N equals 0.0112 moles argon. And then argon is 40, I guess 39.95, I think. So just times 39.95 grams per mole. 39.95. That's right. Let me check. Argon, 39.95. Is in fact correct. So 0.449 grams of argon. That's the answer. Okay. Recap. We have three gases, helium, and argon, in a 1 liter vessel. Total pressure 662 millimeters of mercury, 298 Kelvin. We know the pressure of neon and the pressure of helium. We know the total pressure. We want to figure out what the mass of argon is in grams. So what we do is we figure out the pressure of argon by taking the total pressure minus the other two gases. And then from that pressure, we can find the number of moles of argon, find the number of moles of argon, multiply by 40 grams per mole to get 0.449 grams of argon. So, questions with how to do this? Okay, so let's talk about good old dry air. So depending on where you're at on Earth, the atmosphere has about 1% water in it. So we're probably about that here. If you go to a desert like Las Vegas, there's going to be less water in the air. If you're going to go somewhere where it's really humid, like Florida, if you've ever been to Florida, it's really humid. It's going to have a little bit more of the water in the air. So, but if you look at, take all the water out of air, this is what air is made of. It's made up of about 78% nitrogen, which is mostly inert. It can react, doesn't frequently react though. At least at this temperature and pressure. Raise the temperature, it'll react. Also, lightning bolts. A lot of lightning bolts, they crack nitrogen, and that's how we get nitrogen in our soil. 21% oxygen and 0.9% argon. So the Earth is the only planet that we know of that has a large amount of oxygen in its atmosphere. So if you look at the planet Mercury, Mercury has 35% oxygen in its atmosphere, but it's really thin. And that oxygen just comes from the sun beating the heck out of the planet, just so close to the sun, and it's ripping the oxygen off the rocks. But here on Earth, we get our oxygen mostly from algae. And it's projected that in the next decade or so, many astronomers believe that we will verify that life is on other planets because we will find a Earth-like planet that has oxygen in its atmosphere. So that's what they're hoping to find. They're looking at the exoplanets outside of the solar system, looking for oxygen. And oxygen is a weird gas because it's extremely reactive. So it's very, very reactive. And I'm thinking that oxygen in the atmosphere will verify plant life. That's not entirely true, though. If you're a Star Wars fan, you know what Tatooine or Jakku is, the planets like that. They could have. You can get oxygen in the atmosphere without plant life. I went to a scientific talk about the planets on Star Wars. That could be from if you have a planet that's full of water with a star that's close by that's spewing off radiation, could crack the water into oxygen and hydrogen. Just don't light a match because then the whole atmosphere will explode, of course. But well, then it could happen that the star would crack water into hydrogen and oxygen, and then if the planet was small enough, the hydrogen could leave the orbit, so you get a planet with an oxygen atmosphere that way, or a moon or something like that. That's possible. So if we do find oxygen outside of the solar system, that'll be another great debate. Is this life or is it Tatooine? We'll see. And argon, so argon being about 1% of the atmosphere, it actually it can muck a lot of things up. So recycling makes a lot of sense. You know, another surprise thing you learn in chemistry class. Recycling, it makes sense. So when air is used as a reactant for chemical vessels, anything that doesn't react, people wanted like, oh yeah, there's reactants in here. Let me just put it right back into the apparatus, so I don't have to put more stuff in there. I can recycle it. If you do that, what happens is the argon starts to accumulate inside the vessel, and then your reaction rate starts to drop. So what they actually have to do is, if you have a reaction vessel, you have to purge the line. You have to, if you have air as an input, you actually have to purge the gas out, and that's to prevent accumulation of argon into the reaction vessel, because this is not very reactive. And then and if you have a reaction vessel full of argon, just nothing will react. So unfortunately, we can't, because of that good old argon, we can't recycle our air continuously all the time here on Earth. So nitrogen I'm okay with because it's plant food, right? But argon, we don't really need argon, unfortunately, but it's here. And we have trace other gases, so a particular note is carbon dioxide, but it depends on where you're at. So, I mean, here in Hawaii, we have a little more sulfur in the air because of the volcano. So it just depends. Okay, so I mentioned oxygen. And here is us humans. So we like oxygen. We particularly like it around 0.2 atmosphere, between 0.2 atmospheres and about 1.4 atmospheres. That's our happy zone, maybe even around 1. So this is the safe zone for oxygen amount. So if we have too little oxygen, that's bad. And what's also counterintuitive, if we have too much oxygen, that's also bad. So too little oxygen, this is hypoxia, and below 0.1 atmospheres, you'll die. So, but in this yellow area here. Depends on who you are. I get altitude sickness. About 8,000 feet, I feel kind of weird. So it takes me a while to adapt to it. And it takes me a couple hours to be able to go to the top of Haleakala, for instance. I've been up there. But I slept at Hossamer's Grove, and then I went up to 8,000 feet, walked around, up to 9,000 feet, walked around, and then I went up to the top and walked around. Then I was fine. It took me probably about 3 hours from Hossamer's Grove. I've been to the top of Mauna Kea briefly, and I felt terrible. So took me back down, gave me lots of water, and I was fine. Okay, but that's, most people feel kind of crappy up there anyways. You feel kind of, people tell me, like, I felt terrible, but people tell me they feel kind of drunk of sorts. Okay, this is pure oxygen. I've never breathed pure oxygen before, but apparently people tell me it feels awesome. And then you get to 1.4 atmospheres of oxygen, and this is your maximum that you can do in exertion, and at 1.6 atmospheres, that's the maximum you can do at rest. And if you're in this range, apparently it's really weird. You breathe very, very infrequently, but your heart is pounding like crazy. So, because, I mean, oxygen is one of our fuels, and if you bring in oxygen, you're going to burn it. And so our metabolism shoots up really high in this range. And so can you imagine, like, not breathing or breathing like once a minute, but feeling your heart just pound in your chest? That's what this apparently feels. I never felt it, but apparently that's what it feels like. And why would someone do that? What circumstance could that happen? Well, if you're scuba diving. You're scuba diving, so this is air. So if you were to strap pure oxygen to a tank and go underwater, it'll kill you. Pretty shallow, actually. And here, so at our surface, we have 0.21 atmospheres of oxygen going 30 meters, 100 feet underwater. We're going to have 4 times that in our lungs. So also of note is the partial pressure of nitrogen here. So I don't scuba dive, but people that have scuba dived, they tell me that if you go down deep enough, you get a condition called narcosis, nitrogen narcosis. Nitrogen acts like a narcotic in your bloodstream. So people tell me you feel happy and high. The other problem is with the nitrogen dissolving in your bloodstream, if you ascend too quickly, you can get a condition called the bends. So what the bends are, it originated in the building of the Brooklyn Bridge in New York City, as a matter of fact. So this is back in the 19th century, and the people working deep down underneath the Hudson River, and with all that pressure and the water and whatnot. And this is not today where I've never been in a mine. I would hate to be in a mine. I've been in caves before. I don't even like that. But I mean, really tight quarters. And if you're under the Hudson River, you're gonna have all the pressure from that. And when people were done with their shift, they're like, "Get me out of here! I'm getting out of here as fast as I can. I want to go to the pub and drink my beer and that kind of stuff." And they ascended too quickly. And sometimes when people came up from working under the Hudson River, they went, "Oh, jeez, it hurts to move." And they would, "What's wrong with that person?" Like, "Oh, that fellow there, he's got the bends." Because literally that's what you kind of go in fetal position. It hurts to move your joints, your elbows and knees and back, because bubbles of nitrogen form in those areas. And that's why we call it the bends. And it can kill you, it can paralyze you, it can cause bad joint damage. Did you have a question? Or? Oh, you're okay. Yeah. So if you ever wonder where the bends came from, there's a way around it. You can use a mixture called heliox. It's a mixture of helium and oxygen, and they typically lower the concentration of oxygen for this reason on the board there, like 15 or 10% oxygen. So when people go underwater, they can go deeper. And they might even have more than one gas mixture, so they might have like 10%, or like start with a 15%, and switch to 10 or 5, depending on the depth. And the other gas would be helium, because helium does not dissolve in the bloodstream as much. So it's unlikely you'll get the bends from helium. And I don't think their voices sound high-pitched either. I think that's just here at the surface. I don't know. But, okay. Hopefully this is an easy question for you. Air is 78% nitrogen. What's the partial pressure of nitrogen at 1 atmosphere? I know it should be Y, but... All right, how many think it's 0.78 atmospheres? How many think it's 0.22? I think it's 0.39. How many think you can't tell? So what's 0.7, well, or what's, let's give it away. 78% is 0.78 in fractions, and then 1 atmosphere. So it's this one. And that's, I know I changed topics, but that's from this equation right here. Okay. So how are we doing? Questions? Oh, and I've uploaded all these completed sheets to the La Lima, and all the lecture archives are there. And I'll go over the old test on Monday, and I'll be doubly sure to upload that as fast as I can so you can study from it. So, but all right, so we're in. I think we're gonna have some time to go over some problems, and although it's gas law related, but it's also has the chemical reaction stuff. But we'll get there in about 20-30 minutes. Okay, so next concept I want to talk about is something called vapor pressure. It's inaccurate, but it's described as, so if you have a liquid, so in this case this is water, the idea of vapor pressure is that there is a pressure that the liquid exerts on the surface of the liquid. Things that have very high vapor pressures are said to be very volatile. So I have 3 sisters. I always hated it when they painted their nails. So if you ever smelled nail polish or nail polish remover, right? So it's a liquid, and at least the nail polish is a mixture, but it's the solvent that comes off. So when you open something like nail polish, you can smell it, and if you let it sit for a while, all the liquid will evaporate and it'll dry. So same thing. The idea with that is that the particles in the liquid, the molecules in liquid, can evaporate. It doesn't necessarily have to boil, but it will evaporate slowly. And the reason why it evaporates slowly is because of this vapor pressure. What's really going on not next class, Monday, but I guess a week from Monday, we'll talk about kinetic molecular theory. So temperature means average kinetic energy. It's actually a range. It's not just one energy. It's a distribution. And so at a given temperature, there is a fraction that have a lot of energy. So the fraction that has a lot of energy are able to break the water bond. They're able to go and vaporize. And at a higher temperature, there's more of a fraction. And come on in, you're good. And so the other thing to note, what's going on here is a dynamic equilibrium, meaning that as particles are evaporating, some are also condensing down. So it's not just they're all not just a couple fly and they bounce around. It's a dynamic equilibrium. There's lots of stuff going on. So, and we're going to do a problem about this pretty soon. But okay, and in this case here, so we've got water here, we've got a vessel that's filled with water, and then we have hydrogen gas going into this space in between it. But in the space between it not only has hydrogen gas, but also has water from the liquid, from the water that's sitting there. And here is the vapor pressure versus temperature data. So if you look at these, the next problem is going to be at 20 degrees Celsius, but varying degrees. So, and the vapor pressure, the other thing with liquids, so when the ambient pressure equals the vapor pressure, the liquid will boil. So for water, it has 760 millimeters of mercury, that's 1 atmosphere. Water has a vapor pressure of 1 atmosphere at 100 degrees Celsius. So that's why here at sea level, water boils then. But if you go up in altitude, water will boil at a lower temperature. And if you look at some old cookbooks, so certain things like if you make beef stew, where it simmers the beef, so the simmering temperature changes by your altitude. So it'll say things like, if you have a mile of altitude, add 20 minutes to the simmer time. And the reason for that is that so when a liquid is boiling, the temperature inside the liquid does not change. So the temperature at the walls can change, but inside the liquid, the temperature does not change. And for meat and whatnot to be considered safe to eat, it needs to be heated to 165 degrees Fahrenheit. That's when most pathogenic bacteria are killed. So there are some bacteria that are not killed at 165 Fahrenheit. And those are known as thermophilic bacteria. They're found in like the volcanic waters around here. So those are hard to kill. Those are really sturdy bacteria. Those are really hard to kill. But the stuff you find in food, you heat it to 165, it'll kill most everything. So since the water boils at a lower temperature, it takes a little bit more time to reach that 165. You can look at it the other way around. If you have a pressure cooker, the way a pressure cooker works is that it increases the pressure inside the vessel, so then the boiling point of water goes up. And it requires less time to cook the food. So that's the other way around, pressure cooker. Okay. So similar to this figure here, so look at this beautifully drawn figure, and this looks exactly the same thing, right? All right. So this problem here, in order to determine the rate of photosynthesis, oxygen is emitted by an aquatic plant, collected over water, temperature at 293 Kelvin, also 20 degrees Celsius, and a total pressure of 755.2 millimeters of mercury. Over a specific time period, 1.02 liters of gas is collected. What mass and oxygen is formed? So I'm assuming it's algae, just because aquatic plants, probably algae. So if some algae here, it's in water, and then oxygen bubbles up here, and then we have 1.02 liters. So, but this volume is not just all oxygen, there's also the vapor pressure of water. So here, the total pressure is going to be the pressure of O2 plus the pressure of the water vapor in there. And also, what we're going to do then is get the pressure of O2 to get the moles of O2. Then we can get the mass of O2 from the moles of O2. And we'll get the moles of O2 by the ideal gas law. So if you're wondering how to solve this problem. Okay, so this pressure also implies that the pressure of oxygen is equal to the total pressure minus the pressure of the water vapor. So total pressure is 755.2 minus 17.6. So where am I getting that? I'm getting that from this chart here. So 20 degrees Celsius is 17.55, or rounded up to this 17.6. Then what is that? So 755.2 minus 17.6, and I'm getting 737.6. So PV equals nRT, which implies N equals PV over RT, which is 737.6 millimeters of mercury. Atmosphere is 760 millimeters of mercury. Volume is 1.02 liters. R is constant, 0.08206. Liter atmosphere, mole Kelvin, 293 Kelvin. Okay. I'm going to zoom in for you. You guys are looking, see some people squinting. So, divided by 760 times 1.02. And I'm getting 0.0412 moles O2, and then 32 grams per mole. One point 32 grams oxygen. Okay, recap on this one. We have an ambient pressure of 755.2, and we have algae in here. It bubbles up to form oxygen in this vessel, and so we have an oxygen and water mixture. And then we want to know what the mass of oxygen is in here. So why get the mass of oxygen? So then we can get how much sugar is being produced. So then, okay, so because this is oxygen plus water, we have to subtract the water vapor pressure from the total pressure, get the pressure of oxygen. Then by rearranging the ideal gas law, we get the moles of oxygen, 32 grams per mole, get the mass of oxygen. So, questions with how to do this? $760. Let me make it smaller. You get these numbers. Yeah. It's just this, I found this pen width is the easiest to kind of see on the fly. So when I prep beforehand, then I'll zoom in and make it pretty, but as I'm going, I kind of have to go fast. So, other questions? And the two students that came in, we're having a review next class Monday. I know that the test was originally slotted for today, but it's delayed a week because of the two hurricanes, well, the hurricane and the tropical storm. So if you have not been reading your emails, or have you been getting your emails? Okay. All right. Other questions? Okay, so methanol. Methanol can be made by this reaction. So this reaction here, it's carbon monoxide and 2 hydrogens, so 1 to 2 molar ratio, carbon monoxide to hydrogen. This mixture of gases is known as syngas, synthesis gas, and town gas. We used to pipe this into our homes instead of methane, natural gas. So if you've ever lived on the mainland, you're heating, and some people get their stoves or gas stoves. We have gas stoves here too, but we have propane tanks. But one of my sisters, she gets her gas just from the street. They have gas lines that bring the methane into her house. In the olden days, they used to use carbon monoxide and hydrogen. And that, of course, is a problem because carbon monoxide is poisonous. So lots of people died, and they said, well, maybe we should change to something else. So that's why we use natural gas now. And the other thing with this mixture, if you take this mixture and you mix it over iron and or chromium, you get what's called the Fischer-Tropsch reaction, and you can make all sorts of hydrocarbons. So and Germany did this in World War II. So if you know your history, the Nazis were pushing towards Stalingrad, also now known as Leningrad, because they were going for the oil fields. So they wanted that petroleum. I don't know, Norway has a lot of oil. I don't know why they went just north, but they're going towards Stalingrad, or the oil fields. But Hitler was running his war machine off of synthetic fuels. So he ran it was completely alternative fuels. And he made all his fuels via this way. I mean, it can make methanol, but it can make other things too. And if you look at synthetic fuels, they're clear. So if you ever look at gasoline, it looks kind of like apple juice, kind of, sort of. But if you look at synthetic fuels, they're clear, and they burn with really little soot. So the Royal Air Force, they use synthetic fuels in their planes. The United States doesn't claim to use it. So we probably do in our stealth fighters. I would imagine we do. But they don't. The fuel is very secret, what we use in our stealth fighters. The miners loved this stuff because if they're using the machines underground, it didn't create that much soot. So they liked it a lot better than the other stuff. This put the United States at a disadvantage. Our tanks ran off of gasoline, and the Tiger tanks that the Nazis were using ran off of diesel fuel. So the American tanks were much easier to destroy because of the high octane gasoline. You hit it with a couple bullets and it's only going to blow up. Apparently Zeros were like that too. The Japanese aircraft, if you hit Zeros a few times, they would blow up too from the gasoline. So, but then the Germans, they were using their synthetic fuels. And also, if you know your history, in South Africa around the year 1970, there was a situation called apartheid. That's where there was the legal segregation of whites and blacks. And this didn't sit well with the world, so the world basically said, all right, South Africa, with you and your apartheid laws, we're going to put an oil embargo on you, and you're not going to get any energy. South Africa's response was, screw you, world. We know about the technological advances of the 1940s, and we can make our own fuel. We have coal and natural gas. We'll just make our own fuels. And they do. So South Africa uses synthetic fuels, and they're energy independent. And there's a company called Sasol that does it. So we could get rid of our addiction to oil because our infrastructure is all built on oil. We could switch over to synthetic fuels, but we just don't want to, really. So the other thing, methanol. This is in fact how we make methanol. Methanol is also referred to as wood alcohol. So ethyl alcohol, the stuff you drink, is also referred to as grain alcohol. And you can get grain alcohol from fermenting grains. And then you're like, well, where do you get wood alcohol from? You can get methanol, although it's a mixture of products, by a technique called pyrolysis. So if you take, imagine having like a metal cylinder that closed, like a jar or something, like a metal jar. And inside this metal jar, you put wood in there. And you screwed it tight, and then you threw it onto a campfire or some source of heat, or put it underneath a flame. Then what happens is this chemical reaction called pyrolysis, and if you opened up screw the top open again, there would be like this kind of black tar substance, and a liquid would come out. So you could pour liquid out of it. That liquid, among other things, contains methanol. It's not pure methanol, but it contains methanol. So pyrolysis, that way using the absence of oxygen, heat things up. We're looking at that as an alternative fuel source. So something like plastic, you can take that and you can do pyrolysis and get fuel property from. You can take that stuff, you can burn it. Also, though, I told you with this stuff with the wood, we put the wood and do pyrolysis. It's a big mixture of things, and they can separate out into different things. One of the things that they can get out of that is liquid smoke. So if you ever go to the grocery store and buy liquid smoke, like if you want to make your own, I don't know, like Kahlua pork or something like that, and you don't want to do an emu, you can do it in a crock pot and put in some liquid smoke and just come back 8 hours later. That's how they get the liquid smoke, is they take the product from pyrolysis of wood and they refine it, and voila, you, among other things, you get liquid smoke. You don't have any methanol in liquid smoke, so don't worry about that. So they take all the methanol out. So, but I don't imagine you would drink a whole large amount of liquid smoke anyways. That would be, smells really strong at least. Okay, so, but we're gonna go ahead and do this problem. The other thing to note, temperature 35 Kelvin, pressure of about 1 atmosphere, making 35 grams. This in industry, this would be 1,000 Kelvin and 100 atmospheres of pressure. It wouldn't be this low. It would be much higher. But this is probably a chemistry class demonstration, and I'll just go ahead and do it. So what volume of hydrogen gas at this temperature, at this pressure, do we need to make this much methanol? Okay, so the idea here is we're combining, so gases and chemical reactions, we're combining the concepts from chapter 4. So this is one of the reasons why people hate chemistry, is that you cannot forget anything that you've learned. So all the stuff you've learned in chapters 1 through 3 are needed for the rest of the chapters. So you will forever be doing mole calculations, you will forever be looking at chemical equations and balancing them and getting relationships from them. So, okay, let's do this. So, so what we're going to do is get the mass of methanol. This will give us the moles of methanol. From this, we'll get the moles of hydrogen that we're looking for, and then the moles of hydrogen, we use ideal gas law and get the volume of hydrogen. That's kind of where I see this going, at least. So 35.7 grams of methanol. And methanol sometimes is written as this, NeOH. But I'm not going to write it that way just yet, but because the Me means the CH3 group, the methyl group. Okay, mole CH3OH. So let's see here, 12 plus 4 plus 16, that's 32. 32 grams CH3OH, is that right? So, yeah, that's right. And then 2 moles hydrogen per mole CH3OH. And I'm getting this step here, not the CO. I'm getting that step there from that relationship. Well, you see that there, so like that. Is everyone okay with this setup so far? I'm sorry, what? So CH3OH, there's 12 carbon, 1 carbon for 12, plus 4 hydrogens that are 1, plus, I guess I should have it backwards, plus 16 for the oxygen. So 16 plus 4 is 20, plus 12 is 32. Other questions? Okay, so, oh, I already have that up there. And this is 2.231. I guess I didn't take this down from last semester. And so we have moles hydrogen, so now we have next PV equals nRT, or what do we say? We need volume in liters. So volume is nRT over pressure equals N is 2.231 moles are 0.08206 per atmosphere mole Kelvin. 355 Kelvin. All over pressure. Pressure is 738 millimeters of mercury times atmosphere over 760. And if you do all that, you get 66.9 liters. And the calculator is right there. Okay, so a recap for this one. We have this reaction here making methanol from synthesis gas. And then how much hydrogen do we need in volume if we need this much product and we have this temperature and pressure? So we take the mass of the product to get the moles of methanol, and then by the chemical reaction, figure out the moles of hydrogen that we need for that reactant, and it's 2.31. And then by using the ideal gas law, we can solve for the volume, put in the terms that we know, and we get 66.9 liters. So, questions with this one? Okay, so then the rest of the class, last half hour, we're going to go and do like an emporium model. So we're going to solve problems. And so there's two problems to solve. One is just like the one we solved. It's a chemical reaction problem. The next one is a limiting reagent problem and percent yield. So we will do them both, and we have lots of time. So although the gas law stuff is not on the first test, the chemical reaction stuff is. So first problem. Airbag volume is 11.8 liters. So actually I should back up. Has anyone ever been in a car accident and the airbag deployed? It's happened to me. Oh, so no one has. You guys are all lucky. Okay. So I'm a big guy, you know, and I've got long arms, so I sit pretty far back. And actually the airbag didn't even touch me. I was in a big car accident. The airbag didn't even touch me. The seatbelt caught me. I was wearing my seatbelt. But the airbags deploy, and it's just kind of like it's like a mesh sort of pillow, and among other things is white stuff comes off. What that white stuff is, so let me, how an airbag works, it has sodium azide, NaN3, and this stuff, if you punch it, like if you tap it, it's not going to explode, but if you punch it, it'll explode. It'll turn to sodium metal and nitrogen gas. So what fills the airbag is nitrogen. The sodium metal oxidizes really quickly to form sodium oxide, and I got some on my skin, and they gave me a chemical burn. Some people get it in their eyes. Some people breathe it in, and they can get, if they breathe it in, you can get pulmonary edema. That's when you get fluid in your lungs. So I was lucky, I guess. But either way, so the volume in the airbag comes from the nitrogen. So this is airbag volume is 11.8 liters. That 11.8 liters comes from the nitrogen gas. How much sodium azide is needed for an airbag at one pressure, pressure is 1 atmosphere pressure, temperature is 0 degrees Celsius or 273.15 Kelvin. What mass of sodium azide is needed for that airbag to fill up to 11.8 liters at that volume? I guess R, so PV equals nRT, R equals 0.08206 liter atmosphere over mole. Is anyone stuck and I have no idea what to do? Raise your hand. Okay. Here is a hint in the meantime. guess it should. Specifically, that's moles of nitrogen. Yeah. So you can figure out the moles of this, and then because of the 2 to 3 ratio. So what's the answer to that? Yes. Is in fact 23. Setup is here, and what students have the most problem with is that you have this equation. It's asking for the mass of the azide, and you're given a volume of air. It's the nitrogen that fills the air bag. It's the gas. So 11.8 liters of gas turns out to be about half a mole, and half a mole. Then you have the 3 moles nitrogen to 2 moles sodium azide NaN3, and then the mass of sodium azide, it's 65 grams per mole. So half a mole times 2/3 times 65 gives you 23. Questions with that? Okay. Last problem. So we have methane plus water making carbon monoxide and hydrogen. So this is actually one of the few times the book is right. This is actually how we get a hydrogen, is by steam reformation. All gases. So we have methane, CH4, we have 25.5 liters at 732 torr and 25 degrees Celsius. Water at 22.8 liters, 702 torr, 125 degrees Celsius. Makes hydrogen at 26.2 liters, 760 torr, 0 degrees Celsius. What is the percent yield of this reaction? And so, what is this? This is a linear reagent problem, and you get a product. So then you have to figure out how many moles you should get versus how many moles you do get to get the percent yield. Okay, anyone guess what the linear reagent is? Is it obvious? So which one do you have more of? It's a 1-to-1 ratio, so methane and hydrogen. So if you methane, you have more volume, you have more pressure, and then you have a lower temperature. you could logic your way. Looking at that, you could determine that water's the limiting reagent by the fact that there's less volume, there's less pressure, and there's a higher temperature. Because, right, the PV equals nRT, so both pressure and volume are lower, so that means that number's going to be lower. And then N and T are on the same side of the equation, so if T is higher, that's going to force N down. If that makes sense. So you could logic your way through the limiting region if you wanted to. Or you could do them both. So PV equals nRT. N equals PV over RT. Right, you can see, the other way you can see N is then proportional to 1 over temperature, which means inversely proportional. Right, so if temperature goes up, N goes down. I'll do it for hydrogen. Memorize it? Good luck. Maybe you don't. In that case, I'm going to drink some water. I mean, not drink water because fluids are not allowed in the classroom. Isn't that right, class? No food or drink allowed in this classroom.
For a test, can we have like a graphing calculator?
Yes. Oh, and I'm going to bring chocolate for you, too. Same chocolate I'm eating right now. Which I shouldn't have bought so far away from the desk. No, because some students get, I don't get test anxiety, but a lot of students do. And chocolate is supposed to help. But Costco's having a sale on Hershey's chocolate, so you're getting Hershey's chocolate. Oh, jeez. I'm losing my pencil. Is anyone getting stuck? Got 3 minutes and change left in class. Alright, last minute before my shut up alarm goes off. Answer C. So, there's a glare here. So we already know water is a limiting reagent. So if you do the moles of water, you get about 0.6 or 0.65 moles of water here. And there's by the equation, there's a 3 to 1 molar ratio. So you make 3 times as much hydrogen. So the theoretical yield is 1.93 moles of hydrogen. If you look at what I highlighted in the pink there, that is the actual yield. That ends up being 1.17 moles. And 1.17 divided by 1.93 is 60%. So, questions with that? Okay. Alrighty. I guess I will see you on Monday. Oh, I added everyone to the other section, and then I put a forum if you wanted to form a study group. So that's optional. You don't have to do it, but if you want to form study groups, that is one way you can do it. Okay, have a nice rest of your afternoon. You're welcome. Oh, I should stop recording.